the structure and torsion of abelian groups along lecture 1.
Thank you. So the games will appear somewhat later in the talk. The talk is really about abelian groups, and I think literally everything I say, if not nearly everything I say, also applies to modules over a discrete valuation ring. So if you like those, you can already start reading those in. I'll mention something about them later. To start with finitely generated abelian group. It is a standard theorem that my 519 class just studied, that it has to be a direct sum of cyclic groups. Many and many a year ago in a kingdom by the sea, when I was a student in my institution's equivalent of our 519, I asked my professor a question that I later learned was considered in some circles to be impolite. When we saw this theorem, I asked, well, what about the non-finitely generated ones? And indeed, in certain circles, like some of the ones she was in, that was considered an impolite question. So I didn't get much of an answer then. I later got a good deal more of an answer, and there are reasons that some people don't find non-finitely generated abelian groups pleasant to talk about. But non-finitely generated abelian groups, there are some noticeable ones. There's the rationals. There's rationals mod Z. There's the Proofer group. Proofer group in particular will show up several times later on. So the first big division point in abelian groups, we say that G is torsion if every element has finite order. We say it's torsion free if no element has finite order. And any abelian group will split as a direct sum of a torsion part and a torsion-free part. So for most purposes, you can treat those two parts separately, and direct sums behave nicely with respect to almost everything. So usually you can deal with those separately and then put them together at the end with no problem. The torsion-free situation is really tremendously depressing. So we do know that a torsion-free abelian group is going to be isomorphic to a subgroup of some direct sum of the additive group of rationals. And you would think that would help. It doesn't. For one thing, it can be a really, really huge direct sum. And that itself can make things unpleasant. But even the rank 1 case, so the number of things in I, the number of direct sum n's that you take is the rank of the group. I guess the minimum number of sum n's that you could take and still have this be true. It's the rank of the group. And even the rank 1 case is really awful. And I'll be precise about what I mean by really awful in a minute, but in understanding how depressing the torsion-free case is, first observation is that even the subgroups of Q are bad. And if that situation could get any worse, you can get rank 2 groups that are not direct sums of rank 1 groups. You can get a subgroup of Q squared that is not a direct sum of a subgroup of Q and another subgroup of Q. And the examples like this are really awful. They are groups that, I think Martin Davis said this about a different subject. These are groups that only their mother could love. So in 1937, there was a classification theorem by Baer of the rank 1 torsion-free abelian groups. And the invariance that you get, I mean, you classify something, everybody's favorite classification to which we all aspire in any classification we prove, the great classification theorem is the classification theorem for real vector spaces. Because you get for each vector space a number, a natural number. And 2 vector spaces are isomorphic if that natural number matches for the two of them. And if they don't match, it's not isomorphic. Well, the invariants you get here are not natural numbers. They are weird. You could say roughly that what you get is real numbers, and two of these groups are isomorphic if the real numbers differ by a rational. It's slightly more involved than that, but in a technical sense it exactly amounts to this equivalence relation. And that equivalence relation is especially nasty because one thing that you'd like to do with the structure theorem is list off exactly one element of each isomorphism type. And if you do that with this equivalence relation, you get a non-measurable set, which is enough to trip anybody's criterion for a really nasty set, for something that you wish didn't exist in the universe. So classification of rank 1 groups is so bad that to classify them you need a non-measurable set. So, starting in the 1930s, a lot of really smart people, Maltsev, Irving Kaplansky, Kurosh, Fuchs, a lot of really good people independently failed to classify the rank 2 torsion-free abelian groups. And this caused people by the mid-90s to start asking why. Greg Horth was one of the ones to start asking why. He actually started out as a professional chess player. He said later on in life that in professional chess, if you're not in the top 100 by the time you're 21 years old, you should get out. Well, he got to be 21 years old and was not in the top 100, so he got out and became a mathematician. And not terribly long after, he showed he was really good at it. And not terribly long after that, he started thinking about why it was so hard to classify the rank 2 torsion-free abelian groups. And he and Simon Thomas working together did a lot of the background on this. Thomas was the one that finally got the big version of the theorem. That a classification for torsion-free abelian groups of rank n plus 1 has to be worse than that for rank n. The invariants for rank n plus 1 have to be strictly more complicated topologically than the invariants for torsion-free abelian groups of rank n. So for instance, for rank 1, you need a non-measurable set. For rank 2, you need something worse than a non-measurable set. Strictly worse. For rank 3, you need something strictly worse than that. And by the time you get to infinite rank, it is just plain ruination. If you could classify torsion-free abelian groups of infinite rank, then we'd have an equally topologically good classification of all groups, or of all graphs. And nobody thinks you can do that. Nobody thinks that they're ever going to get a reasonable classification of all graphs, or of all groups. So I actually had some progress toward this in my thesis, and then Dadi and Montalban finished it up fairly recently. So, for this reason, we will now quit torsion-free abelian groups for the moment, and for the rest of this talk, and talk about the torsion part, which is much nicer. So we have a torsion abelian group. First big thing about the torsion ones is that you can split them as a direct sum of p groups for each prime. And again, you can do things on the individual components and then put them together in a nice way. So it's enough now to talk about abelian p groups. Because if you know abelian p groups for each p, you put them together into an abelian torsion group, and then you know about abelian torsion groups, and then you say, well, if those other people ever tell me anything about torsion-free abelian groups, then I'll know about all abelian groups. So among abelian p groups, we're now splitting farther and farther. Among abelian p groups, the next big dividing line is divisibility. So we say that the group is divisible if every element divides by every natural number. So for instance, in the group of integers, you can't divide 2 by 3 and still be in that group. In the group of rationals, you can divide anything by any natural number you want. We say that the group is reduced if it has no non-trivial divisible subgroup. And again, you get a direct sum. Any abelian group is a direct sum of a divisible part and a reduced part. And the divisible parts of an abelian P group are easy. If you have a countable divisible abelian P group, in fact, it may not even have to be countable, but certainly a countable divisible abelian P group, then it has to be isomorphic to a direct sum of Prüfer groups. And those we know something about. We know what ZP infinity looks like.
Think of it as the set of all P power roots of unity in the circle?
You can. Or you can think of it as a subgroup of Q mod Z, where all the denominators are some power of P. So now we want to know about the reduced part. And there we finally need some actual work. So take a reduced abelian P group. And then you define some sequence of subgroups of it. Start with the group itself. Start with the whole group. At each successor stage, take the stuff in G beta that's divisible by P one more time. Take all the things that are multiples of P in G beta. That gives you G beta plus 1. Now if you have a finitely generated abelian group, then that's as much as you need. You do this, and then eventually you run out of factors. You get past the biggest cyclic group, and you're done. But maybe it's not finitely generated, and maybe you keep doing this forever and don't run out. No problem. Take the intersection of all of them and start again. Take the intersection of all the ones, take all the stuff that you have left at the end of time, and then step omega plus 1 is take all the stuff that's divisible by P in that. For each element, you can track the stage at which it drops out. And each element, if it's a reduced group, each element is eventually going to drop out at some point. That we call the height of the element. And eventually, since it's a countable group, eventually everything's going to drop out. And that we call the length. How long this system keeps going before you get down to nothing. So now for the actual classification. For each alpha, take the things in G alpha that are P torsion. Things in alpha that, if you add them to themselves P times, you get 0. That is going to be a Z mod P vector space. And if you take the factors in this sequence, P alpha mod P alpha plus 1, that's still a Z mod P vector space. Take its dimension. That's the big deal from this page. This sequence of U alphas is what 85% of the rest of the talk will hinge on, is these dimensions. And the reason that it hinges on them, before I get to the reason, an example. I defined too many things on the last slide not to give an example. So take a familiar abelian group, Z2 plus Z4. And I've marked the generators in each of them. So G0 is the whole thing, and the P torsion parts of that are the generator here and 2 times the generator here. G1, well, nothing here is divisible by P one time. The 2 in this group is divisible by P, 2, divisible by 2 ones. So that's G1, and everything there is P torsion. So we still have that's P1. And by G2, we've got rid of everything. And so if you look at, let's see, so P naught, U naught is P naught mod P1. We have 1 dimension there. So the first Ullmann invariant is 1. Take this factor, 1 dimension there. Second Ullmann invariant is 1. Everything else, 0 dimensions. So what this tells you, and this is always true when you have a direct sum of cyclic groups, what this tells you is 1 cyclic factor of type Z mod P to the 1, 1 cyclic factor of type Z mod P squared, and no others. So the Ullmann invariants in a direct sum of cyclic groups, the Ullmann invariants tell you how many summands of each kind you have. Now, if the process takes longer than length omega, it's not a direct sum of cyclic groups anymore, and so you have to interpret these a bit more symbolically. But in an initial segment of the Abelian T groups, it tells you how many direct summands of each kind. And short group or long, if all the Ullmann invariants match, they're isomorphic. If not all the Ullmann invariants match, they're not isomorphic. So there's the classification of torsion Abelian groups when you put all that together. So, measure of a good classification problem is whether you can solve problems with it. A good classification theorem is whether you can solve problems with it. And the kind of problems that I like to solve are computational, algorithmic type problems. So this problem goes back to Dane in the early 20th century. One way to look at it is, given the group, can you actually compute the value of x plus y given x and y? The way he put it is you're given a presentation of a group by generators and relations, and what you'd like to do is take some word in these generators and decide whether it's trivial. It's exactly the same as saying, can you compute the value of the group operation? And the answer is no. Not even with everything as good as you would hope. I mean, if you make some restrictions on the structure of the group, you can get it to be yes. But in general, even for finitely generated groups, the answer is no. But if you put the right restrictions on the structure of the group, you can get the answer to be yes. So a natural thing would be to ask if we could get Abelian groups to say yes. And we can't. There are way too many of them. There are way more Abelian groups than there are algorithms to compute their operations. So then the question is, which ones have solvable word problem? And here I need way more definition than I'm actually going to give. I say that a function's computable if there's an algorithm that will take in the input and give you out the output. There are definitely longer definitions of this that are more technically precise and are useful if you're actually going to prove something with them, but they are not any more enlightening than this. If you could program it in your favorite programming language, and run it on Rachel's computer, it's computable. If not, it's not computable. Okay, maybe Rachel's computer plus a lot of extra memory. Like 1 extra gigabyte for every atom in the universe or something. And you might have to wait a length of time equal to 7 times the age of the universe to get your answer. But if you could do that in some finite time with some finite memory, it's computable. So now the question is, for which Abelian P groups, is there a computable function that will take in a word, will take in this plus that plus the other thing, and will say yes if it's equal to 0 and no if it isn't? Now the way to get a negative answer on any of these things, and that was actually the big holdup for Dane's problems and for a bunch of others, was figuring out a way to express a negative answer. And the start on getting a negative answer is to remember that since the von Neumann architecture in the late 1940s, a computer program is data. Those of you as old as me will remember dark days at the beginning of time when computer programs came on these disks. And this disk would have the data written on it for the program. You would put it into your computer, and it would whir and whir and whir and make all sorts of horrible noise, maybe even grunt a few times. And the computer would read the data off the disk and execute that data as a program. So, in principle, that data that constitutes the program could be given as input to another program. In fact, that's just exactly what an operating system is. So, you have this halting set, which is familiar to regular attenders of our colloquium. The halting set is the set of programs that, when you give them themselves as input, they will successfully terminate. They will not get stuck in an infinite loop. They will not crash. They will not melt your computer. They will not send up an error message and quit. They will successfully terminate and do something. And the characteristic function for that set is not computable. I sometimes call it the Microsoft Windows problem. You're using your computer, and it jams. And you wait for a little while to see, maybe if I wait a little bit, it'll resolve itself. Maybe it'll start working again. And it doesn't start working again, so you wait a little longer. And if it ever does start working, then you'll know that it started working again. But you never know for sure that it's not going to start working again. That's exactly the problem here. You don't know if something is going to terminate if you wait just a little longer. So that's the benchmark for negative solutions. And you can make more benchmarks in the same way. So take a set. We read this X jump. So now, instead of just a program, you let this program have access to a database. And this database will tell it everything it wants to know about X. The program, in the course of running, can get to a point where it would know what to do if it knew whether n was in X or not. And so it checks it in its database. Is n a member of X, yes or no? And then acts accordingly. So you take programs with that kind of data and take the halting set among those programs. That we call X jump. And that kind of program, by the way, we say that the function's X computable if it's computable by a function that has that kind of access to X. And the idea of this jump is that you start with the empty set, because the empty set gives you no information at all. The empty set jump is exactly the halting problem, because it's the programs with no database that halt. And then you take the empty set jump. And that's strictly harder than empty set jump. each jump is harder than what you're jumping from. So here's the solution to the word problem on reduced abelian p-groups, at least such of it as we have. And the state of this is unsatisfactory. This theorem should be stronger than it is. So take a reduced abelian p-group with length less than omega squared. And that's the first thing I have a problem with, is the length less than omega squared. Because omega squared is not that special as transfinite ordinals go. Take a reduced abelian p-group with length less than omega squared. Then it has solvable word problem if and only if we have a certain collection of gadgets. First gadget that we need to have is a thing, never mind that part for the moment, a thing that lists off the pairs in K where the something plus nth Ulm invariant is at least K. So if I equals 0, if you're talking about just the length omega things, if you're looking at I equals 0, you're saying there should be at least K direct summands of type Z mod P to the n plus 1. You need information about those. And it has to be computable from the 2i plus second jump of the empty set. Second thing you need is another thing that's computable from some jump of the empty set, a particular jump of the empty set. And it's a weirder function. What it's supposed to be telling you in the end is someplace beyond where you are, something greater than n where you have a positive Ulm invariant. And what this function should be, it should be a function in two variables, and it should be monotonically non-decreasing, and the limits for each n, the limit should exist and should be greater than n, and that limit is the thing that tells you where to find a positive Ulm invariant. What this really does is, if you're trying to compute something in the group and make a mistake, you need something big enough that your mistake won't be noticed. You need to be able to say, well, really I wasn't trying to compute that thing. I was trying to compute this other thing. And you need something else big enough that you can make that switch. That's what this thing tells you. But the form of it, about this monotonically non-decreasing with limits that do this and that, that's actually an interesting feature. And the maybe first slide of another interesting talk that I could give that I think some of you have heard about distance functions and graphs. There you make it non-increasing, and this binary function, well, I guess it's a ternary function then, is telling you the current estimate of the distance between these because you're looking for a shorter and shorter path. But that's another talk. Big open question is what happens for the longer groups. Everything written here, there is a natural way to write it. The theorem would make perfect sense if you said it without the lambda of g less than omega squared. I mean, you might have to touch up a few points, but there's nothing essentially wrong about the statement of the theorem as far as anybody can tell. The smart money says that the natural way to tweak this around should still work beyond omega squared. Kizeniev's proof really does not work for length greater than omega squared. And a lot of really smart people have spent a lot of years trying a lot of times each to make this work for length greater than omega squared with no hint of success. I should mention, I promised some academic intrigue. This result is, as I say, due to Nazif Kizemiev. At right about the same time, there was I don't remember if she was a graduate student just finishing at the time or an early stage postdoc, but there was another person in the US that proved this theorem, the same theorem using almost exactly the same proof. Slight cosmetic differences, but only that. In those dark days, and even more in the dark days that preceded them, Russian mathematicians did not talk to American mathematicians, and American mathematicians did not talk to Russian mathematicians. This is a slight overstatement, but people did not go to the same conferences. People did not publish in the same journals. Well, it's 1992, so people certainly didn't email one another. People worked in general ignorance of what was being done on the other side. And so, I think this is the last big example I know of, but from the 1930s to the 1990s, there was this big long string of results that now have two names next to them, because 30 years after the fact, after it was well known as a result of Tarski or Church or somebody, or Kleene, 30 years after it was well known as a result of Kleene in the US and well known as a result of Kolmogorov in the Soviet Union, 30 years afterward, somebody would realize that they had both proved the same thing. So it'll now have two names next to it. Now, with Sarah Oates, we weren't quite so fortunate because she had this thing that got caught by an editor where she had submitted it. She had another two papers that got enmeshed in editorial mishaps, and so got bogged down and weren't able to get published for years and years. And so, well, and it was the early 90s, which were dark times for employability in mathematics. And so, in the early 90s, not long after this, Sarah Oates finished her postdoc and became an actuary. So, now for the games. So, you can actually do this, and I mean to do this with Abelian groups. Linear orders are a little easier to see, especially dense linear orders. So dense means you have 2 points, there must be another one in between. So we'll play this game. First I'll pick some elements. I'll pick some elements of L1 and some elements of L2. And then you pick some elements. You pick some y1 and so forth to match my x1 and so forth. Pick some x1 and, or xk plus 1 to match my xk or my yk plus 1. You try to match mine, and then I pick some more and you pick some more. You win if what we get is an isomorphism. And if we have two dense linear orders there, you're guaranteed to always be able to win. Because whichever ones I pick, okay, they're going to set out some finitely many intervals. And then there are some more that you have to match. And to match this one, you check which interval it falls in and put it in the corresponding interval on your side. And then you can squish down or stretch out any intervals you want, because it's all dense, and stretching or squishing doesn't matter anyway. The way you could wind up losing this game is if we change the structure. If we have a dense linear ordering on one hand and the natural numbers on the other hand, then the first thing I'm going to do if I'm trying to beat you at this game, the first thing I'm going to do is name 0. I'm going to make you pick some place that 0 has to be mapped under this putative isomorphism. And the moment you say where it goes, then I'll pick something less than that, and you won't be able to match it, you'll lose. Now, since these games can be long, let's program a computer agent to play for you. This computer agent is trying to build something that could potentially be an isomorphism. And the big thing for the computer, the hard thing, would be searching for the elements it wants to pick. And if it's going to play well, what it should do is search for an element such that whatever I pick next, it will have a move to follow that. So it needs to search for an element such that for any choice I make, there exists some other choice it could make. So it has to search for each of the all choices I could make. So when you program this thing, there's a question. For each step of depth that you want it to be able to search in this game, it needs to be able to do an unbounded search. It needs to be able to solve the halting problem once. It needs a jump. Because this unbounded search is like looking for that time when your computer starts working again. If you find it, you know you found it and you're done. If you don't find it, well, maybe that's because you haven't looked long enough, or maybe that's because it's not there. So it needs a jump for each level of depth that it wants to search. And you can actually play this game for a limited number of rounds, and that gives the pro-isomorphism player a little better shot, because they don't have to actually make an isomorphism, they just have to make something that is going to keep looking like an isomorphism through so many turns. If they can keep matching everything I say for 15 turns, then maybe we'll say they've done pretty well. Yeah.
Wesley, isomorphism in what sense? I mean, so
if we're talking about linear orders, a bijection that preserves the ordering.
Okay.
Could you please explain once again the game, the picking up and then exactly the isomorphism of what, right?
Okay. So you have these two orders.
Two ordered structures, right?
And your goal in the end is to have this be the graph of a bijection that preserves the ordering. So what I'll do is name some elements on each side that you have to match. And then you'll try to match them. And then I'll name some other ones that you have to match.
What do you mean by match? Do I pick up from the other?
Yes.
Ah.
Yes. So x1, I name an element of L1.
Okay.
And you're claiming that there's this isomorphism.
Okay.
So you have to say where x1 goes under this isomorphism.
Okay.
I name y1, or yk plus 1.
Mm-hmm.
I name an element y in L2, and you have to tell me the x that maps to it. And if you get something that you could keep matching and it keeps looking as if it keeps preserving the ordering for so long, if you can keep playing that game for 12 turns without getting caught, we might say that it looks a lot like an isomorphism. That these two structures are very similar if you're guaranteed of being able to keep this up 12 turns.
So your next step, like next to the next to the next, does not necessarily depend on what you played before. It's pretty random, right?
Well, depends on whether you're playing random strategy or good strategy.
Okay, that's what I want to know.
In particular, if I'm playing good strategy, then I will set you up in the first turn with things that'll be hard to match.
Mm-hmm.
And maybe they're just hard to match in principle. But maybe they can be matched in the first turn, like if you're mapping a dense linear ordering into the naturals. Okay, 0 by itself is not hard to match, and even 0 plus a lot of things greater than 0 is not hard to match. You can do that over here in your dense linear ordering. But after you've done that, after you've said where 0 goes, then I say, well, what about this thing over here? What thing over here in the naturals maps to that? Because this is less than the thing you said was isomorphic to 0. And then you're stuck. And the trick toward proving all remaining theorems in this talk is to not play this on linear orderings, but to play it on Abelian torsion groups, and to say that a computer that has so many jumps can only play or can only see through so many rounds, and so will get fooled by something that's that close to isomorphic. That's so close to isomorphic that you could play 12 rounds and your side would still be alive. So here's another statement of the same game. So take a couple of Abelian torsion groups and some tuples within them. So the one-turn game says any linear equation here has a solution there. Or any linear equation with a solution here has a solution there. So you make up something, maybe say that B1 is divisible by 3. You could write that linearly. 3x equals B1. If your side is going to be able to survive through a turn, it has to be true that if that has a solution over here, then the corresponding thing about A1 should have a solution over here. These strings you could think of as some initial given data. So we start playing sometime into the game.
So I would think, okay, so you have a solution on the B side, and there exists a solution on the A side, so there should be an isomorphism. You should just have to send these to these and we'll be fine. Now, if I compare two of those, it appears that there should still be a way that I've lost the game at level 1, because this equation forces my putative isomorphism to do one thing, and this one forces it to do something contradictory. Is there a way to make that like a 2-equation contradiction into a 1-equation contradiction?
Yes, I think there is. I think, I'm not sure I'd be able to say it just right whilst plugged in, but I think that can be done. It may be that doesn't show up until 2 turns in, but I think what you said could show up at 1 turn. So if you have something greater than 1 here, greater than 1 turn, maybe some transfinite number of turns, I don't know. The goal is for each subset of this one and each shorter number of turns, because the idea is that I'm going to pick some challenges, and there are only n-1 turns left that they could be proved wrong in. So for each beta less than alpha, there should be a match that matches up to some lesser number of turns. So now, the challenge is to see whether these things have any algebraic meaning in terms of the Ullmann variance. Because if you can express these in terms of the Ullmann variance, then you're off to the races. Now, the version I'm going to say here is for an even number of turns. Barker also proved this for odd numbers of turns. And in every important characteristic, the two are the same, except the odd number of turns takes a lot more writing and a lot more attention. So, first criterion for these two, for A to be 2 alpha less than B, is that the map that matches the corresponding elements of the tuples extends to an isomorphism of these 2 finite subgroups. Because everything's torsion here, remember. And it's not hard to check whether you have an isomorphism of 2 finite things. And the second criterion is that if you take x in the subgroup generated by the tuple B and its image, then the heights should match if they're less than omega times alpha, or they should both be bigger than omega times alpha. If the way of thinking of this is that if alpha many turns is enough to distinguish, then they should have the same height. Or at least they should agree that alpha many turns isn't going to sort it out. The heights speak to how divisible things are. So now, we're up for another question. Actually, Ohm's theorem can be proved from this, because the two groups are going to be isomorphic if and only if you could play as many turns as you like, and the pro-isomorphism player is always going to win. And these are the conditions for when that can happen. So, next test problem. If I have a particular reduced Abelian P group in mind, how hard is it to recognize it if I saw it again? And the right way to say how hard it is, at least in my world, is to say, well, I could recognize it if you gave me 287 jumps. Then I would have a computer powerful enough to recognize it. So, if you have a reduced Abelian P group of length so much, and notice that we're still below omega squared, exactly because of the hang-up with that Kissimiev result, then to recognize another copy, well, depending on what the element variants are, it's going to be either 2m plus 2 jumps, or 2m plus 3 jumps, or 2m plus 4 jumps, depending on whether the element variants up top are finite or infinite or zero. And actually, you can distinguish a little bit more sharply among these cases, except that you need more computability theory to express those distinctions, but you can prove sharper distinctions there, and we did. And the proof in all these cases is that you test the problem of recognizing A again when you see it by building another group that is so much like A that too weak a machine can't see through enough layers of the back and forth game. A machine weaker than these would not be able to see through enough layers of the back and forth game to tell that these two groups are different. From as many stages as it could play, they'd look like the isomorphism player will win. Next problem to use this machinery on. I have two groups and I know they're isomorphic. Now my favorite example of this is not with groups, it's with fields. Take any two algebraic closures of the same field. You know they're isomorphic. You can prove that they're isomorphic. And the proof goes something like, insert big long list of setup things, and then you apply Zorn's lemma, and it's magically true. This is not a satisfying way to say that things are isomorphic. In particular, if you asked your computer to compute this isomorphism, you wouldn't be able to do it. So I'd like to know whether I can compute the isomorphism between these two Abelian P groups. And here's another one of those east-west results. The answer is yes. If you have any number of copies of the proofer group and then some finite thing added onto it, or else you have some finite number of copies of the proofer group and some finite thing, and then infinitely many of one type of cyclic summand. And the proof here is that you absorb all of this finite group, or maybe all of this finite group and one marker in each copy of the proofer group, you give yourself that much data to start off with in playing the back and forth game. You can match a finite thing. It doesn't take much computation to do that. You can just look that up. And then once it has that finite bit, then a computer can actually play the game well enough after that, if you give it that finite startup. Otherwise, it can't. But, doing one unbounded search, saying that you compute an isomorphism by find an element in G2 that has this property, that we usually don't think of as enormously hard mathematical heavy lifting. Yeah, a computer couldn't technically do it, but we normally feel comfortable saying that. So that corresponds to giving one jump. And then the answer splits into a whole bunch of cases which are technical to state, but they're all stated in terms of if the Ullmann variants are thus and so, then this way. If the Ullmann variants are this other way, then that way. With the exception of two cases, both of which are horrible and technical and great open problems, with the exception of those two open cases, you can answer the question for that. And of course, we'd like to know about the remaining two cases. One of those two cases is also the one dangling open case of several other well-known open problems. It corresponds to when those limit-wise monotonic functions, those FIs that are monotonically non-decreasing in the second argument and have limits, it has to do with weird behavior of those things. That's one of the cases. Last problem. When I was in India, I took to drinking coffee with various people, including one algebraist. And this algebraist said to me, I have these couple of problems, and I know there has to be some connection between them, and I don't know what. And so we started looking at them. One is take this finite Abelian group and classify the orbits of the automorphism group with it. Second case, take this field and classify the orbits of the automorphism group of it. And we got to working on it. I should tell about the n=1 case. So if you're talking about just automorphism types of single elements, then what you do is you say that element A degenerates to element B if there's some homomorphism that takes A to B. So it doesn't have to be an automorphism, just some homomorphism. And this property is invariant under the automorphism group. If two elements are automorphic, then they degenerate to exactly the same other elements. That's as it should be. This part is a little more remarkable, that if you have degenerations in both directions, then there's some automorphism that takes one to the other. This is not always true in structures in general, but for this kind of structure, for these finite Abelian groups, it's true. And so by looking at the partial ordering that you get from that, you can actually count how many elements are in it, and you can count the orbits. And that they had done before. Yeah. If anything about valuations makes you uncomfortable, pretend I didn't say it and pretend I'm talking about Abelian groups. Ohm's theorem works perfectly for torsion modules over a discrete valuation ring. Barker's theorem characterizing when the isomorphism player can win the back and forth game works for modules over, torsion modules over a discrete valuation ring. Don't need that. What I need is the theorem. So you have a homomorphism of modules over a discrete valuation ring or of abelian groups, then the height has to go up. An element has to be sent to something of height at least as great as its own height. And it has to be sent to something of order no greater than its own order.
What's the height of 0? Because sending it to 0 is a homomorph.
Yeah, 0 I think has infinite height. Because 0 is still around at the end of the game. 0 is still around at the end of that sequence. So from a slight restatement of Barker's theorem, degeneration also partially orders the orbits of tuples. So it works for the thing that makes it possible to classify the orbits of single elements also allows, well, the key lemma also works for tuples. Also subgroups. We don't know what the partial ordering looks like. If we knew what that partial ordering looked like, if we knew its structure as a partially ordered set, then we would have solved the problem. We know stuff, but not nearly enough. Conjecture is that for n equals 2, for automorphism orbits of pairs, there should be polynomially many of them. That's the conjecture. And we also conjecture, in a much weaker sense, that this classification for any n doesn't depend on which discrete valuation ring you're in. If you're over the integers and working with abelian groups, if you're over something else, it's still the same partial ordering, which would explain what the similarity is between those two problems that were posed to me. Yeah, the problem there is realizing the Barker invariance, realizing heights and orders of various things that you can cook up from a generating set. Other questions?
Can you go back a few? This polynomial thing, there.
Polynomial thing, yeah.
This,
So I guess there's also an implicit dependence on lambda, on how many summands of each type. But for n equals 1, it's constant. It depends only on lambda.
so I mean, so the right-hand side would appear to either be a constant that it depends only on E.
Yes.
Is there some way to fix A and vary P?
Fix A and vary P.
Or fix G? I guess A is the automorphism group of G. So
G is the automorphism group of A.
Of A.
Yeah.
Okay.
G is the automorphism group of A.
Okay. So
if you fix P, then we're talking about A being an abelian P group.
and I would think that the left side would depend on which abelian P group.
Yeah, it depends, there's also, that's what I was saying, there's also an implicit dependence on how many summands of each kind. But relative to that, for instance, it does not depend on, the big thing is that if you go to count them, you won't get too many. You'll only get polynomially many. Because the worst possible case for structure is that you look at orbits of the automorphism group and well nigh everything's in its own orbit. Very, very regular structure. The old man of Nor who looked the same behind as before. There, the automorphism group is transient. Okay, you're not going to get that with a group, but you can get close to it or far away from it. And what this says is you're not going to get wildly far away from it. You're not going to have too many orbits.
Good fun.
I don't have any further questions.
I think Joe's telephone may be telling us that it's time to go eat. Thank you all for coming.